Petrophysics Daily, your daily petrophysics guide. Imagine staring at a pristine well log printout, right?
Yeah. The dream scenario.
Exactly. The resistivity curve is just, it's spiking perfectly. The density log looks fantastic. The data practically screams pay zone.
It's the kind of printout you want to frame.
Right. And based on this, you confidently sign off on a $50 million drilling operation. You go to the executive board, you promise them a massive new hydrocarbon discovery, and everyone's celebrating.
Until they're not.
Until they're not. Because 6 months later, the bit reaches total depth, the tests come back, and it's a dry hole. Bone dry. Tens of millions of dollars completely evaporated.
It is a nightmare.
Yeah.
And it happens more than people outside the industry realize.
Which is exactly why we are here. Welcome to today's deep dive. We are looking at a fascinating field guide based on Chapter 1 of Elsevier's 2016 textbook, simply titled Petrophysics. Our mission today is to explore exactly why this highly specific discipline had to be invented in the first place, to prevent those exact $50 million disasters.
Yeah. And to do that, we have to dissect what the source calls the 4 controls of reservoir interpretation.
Right, because the central premise of the material today is elegantly stated, but I imagine immensely difficult to execute. It says, rocks tell a story, we learn to read it.
I love that quote. But reading that story in the subsurfaces, well, it's fraught with peril. These 4 controls we're going to talk about, they aren't just academic bullet points. They are a really rigorous sequential safety net.
A safety net to keep your interpretation grounded in physical reality, basically.
Exactly. Because reality in the subsurface loves to throw curveballs.
Oh, for sure. So to understand how we read this story, we first have to look at the historical gap that made petrophysics necessary, right? Like, geologists have understood the structural history of the Earth for centuries.
Right.
And petroleum engineers, they understand fluid dynamics. But for a long time, there was this massive disconnect.
Yeah, a huge gap between knowing the geological history of a basin and knowing precisely what fluids were trapped in the pore space right now, a mile underground.
And that disconnect was basically the breeding ground for those dry holes.
Absolutely. Geology gives you the depositional environment. It tells you how the rock got there, but it doesn't give you the exact saturation of oil versus water in a specific, cubic foot of sandstone.
Which is where petrophysics comes in.
Right. It was developed specifically to bridge that gap. It connects the rock physics, the fluid properties, and those remote measurements we take from the surface or the wellbore.
And the catalyst for bridging this gap, according to the textbook, was Gus Archie in the early 1940s, right?
Archie, yes. The pioneer.
He looked at all these qualitative descriptions of rocks and realized, they just weren't enough. We needed a mathematical relationship between the physical rock matrix and the fluids inside it.
He formalized the thinking. Archie's work laid the foundation for evaluating reservoirs using rigorous physical principles rather than just, educated guessing.
Which brings us to the first of the 4 controls designed to prevent these catastrophic failures, the Archie context.
Yes. And in the practical review path outlined by the text, this first control carries a massive 92% weight.
92%, that is huge. Okay, let's unpack this. We need to clarify what that percentage actually represents, because it's not just a random number.
No, it's crucial. The authors assign these weights to indicate the structural integrity of your interpretation.
So it means that establishing the correct rock context provides like 92% of the foundational grounding for literally everything that follows.
Exactly. If you get the rock context wrong, your subsequent data analysis is fundamentally skewed before you even touch a calculator.
Right. I like to compare it to the setting of a novel.
Oh, that's a good analogy.
Yeah, because if you just read dialogue without knowing the setting, you completely misunderstand the story. The context dictates the physical rules of the environment.
Precisely. If your rock is a clean quartz sandstone, the electrical and acoustic rules behave one way. But if it's, say, a fractured carbonate or a shale laminated sand...
The exact same... Oh, well, log readings mean something completely different.
Completely different. The Archie context forces you to define that physical setting before you try to interpret the dialogue.
But how do we move from just having a context to actually making verifiable claims about what's underground? Let me push back here for a second.
Sure.
We operate in an era of massive computational power. We have neural networks, machine learning algorithms that can process thousands of well logs in seconds. Why is a manual check of the Archie context still taking the top priority? Shouldn't the software just figure out the rock type from the log responses?
is a very common assumption that the software will save us. But algorithms, they fundamentally struggle with non-uniqueness.
Non-uniqueness, meaning what exactly?
Meaning, well, log responses can have multiple causes. A low resistivity reading, for example, could mean you have a water-filled formation.
Okay.
Or it could mean you have a highly productive oil zone that just happens to contain conductive clays.
Oh, wow. So an algorithm looking strictly at the numbers might flag it as water and just abandon the zone entirely.
Exactly.
Yeah.
But a human interpreter, applying the Archie context based on the regional geology, they recognize the presence of that conductive clay. They realize it's actually a massive pay zone.
So the algorithm doesn't know the geological history. It only knows the data. The context gives the data its meaning.
You hit the nail on the head. The context acts as the filter that prevents the algorithm from leading us off a cliff.
Okay, so once we have that solid foundation, we know what kind of rock we are dealing with. We have to move into the actual measurement.
Yes, moving from the theoretical to the physical.
Which is the second control in the sequence, quantitative thinking. The text assigns this an 84% weight.
Right. Petrophysics is fundamentally a quantitative science. The source material really emphasizes that reservoir evaluation absolutely requires measured relationships. You cannot just guess.
The conclusion has to be mathematically connected to the rock properties and fluids. And specifically, the focus narrows down to the pore system.
The pore system, yes. This is where the physical reality of the rock really matters.
So it's not just a solid, impenetrable block of stone. It's more like, well, like a highly compressed microscopic sponge where the empty space is actually the most important part.
That's a perfect way to visualize it. The entire economic viability of a reservoir relies on that empty space.
Yeah.
It's the relationship between the solid rock grains and the pore space containing the fluid.
But it's not just a matter of calculating total porosity, is it? Like, we have to understand the tortuosity, the permeability, how all those pores actually connect.
Exactly. You can have a rock with very high porosity, a lot of empty space. But if those pores are isolated from one another, the fluid can't flow.
It's stuck.
Right, it's impermeable. Quantitative thinking forces the interpreter to rigorously measure that grain-to-pore ratio and the connectivity of the space. You have to quantify the physical container before you can quantify the volume of the hydrocarbon treasure inside it.
But since the sponge is buried deep underground, how do we confidently measure that core space without physically seeing it? I mean, we are talking about quantifying microscopic pore throats.
Yes, on a microsometer scale.
On a micrometer scale. Yet the rock is 10,000 feet underground. The sheer scale difference is staggering. How do we confidently quantify that without a massive margin of error?
And that logistical nightmare is exactly why the third control exists: integrated evidence. This control carries a 76% weight. Because the subsurface is so hidden and heterogeneous, relying on a single type of measurement is basically scientific suicide.
So we need multiple perspectives.
Yes, the guide explicitly states that we have two primary windows into the subsurface, and we must use them both, clearly separating direct evidence from interpreted evidence.
I like to think of this using a medical analogy. Imagine trying to diagnose a complex disease. Direct evidence is like the physical biopsy, right?
Right.
In petrophysics, this is the core sample. We physically cut a cylinder of rock out of the earth, bring it to the surface, and we can put it under an electron microscope. We physically measure the exact porosity and permeability in a laboratory.
It is undeniable ground truth.
But, and here's the catch, a core sample is just a few inches wide.
Exactly. It's incredibly high resolution, but it's fundamentally microscopic compared to the size of a reservoir that might span dozens of square miles.
Yeah, taking core samples across an entire field would be, what, economically impossible.
Completely impossible. So we need the interpreted evidence.
Right. So going back to the medical analogy, if the core is the biopsy, the interpreted evidence is the MRI scan.
I like that. We lower instruments into the well bore to take continuous readings of the surrounding rock formations. These are our well logs.
And integrating those two windows is where the real discipline happens. You use the biopsy to calibrate the MRI.
Exactly. The core grounds the well logs in physical reality, and the well logs extend the reality of the core across the entire vastness of the reservoir. The integrated interpretation acts as supporting evidence.
The text highlights a standard suite of these well logs used for interpreted evidence. It lists them as GR, RES, DN, NPHI, and SUN.
Right, the essential toolkit.
Let's actually dive into the mechanics of those, because I think understanding the physics explains why integration is so critical. Start with GR, the gamma ray log.
Okay, so gamma ray is primarily used to distinguish between reservoir rock, like sandstone, and non-reservoir rock, like shale.
And the mechanism relies on natural radioactivity, doesn't it?
That's correct. Shales naturally contain higher concentrations of radioactive isotopes, things like potassium, uranium, thorium. Clean sandstones and carbonates typically do not.
So, as the tool moves up the wellbore, a high gamma ray reading acts like a radioactive signature for shale.
Exactly, while a low reading indicates a cleaner potential reservoir rock.
Got it. Then we have RES, the resistivity log, which goes all the way back to Gus Archie, right? This is how we distinguish between water and hydrocarbons.
Right. The physical principle is straightforward. Formation water trapped underground is usually highly saline, so it conducts electricity very well. Hydrocarbons, on the other hand, are insulators. They resist electrical current.
So if you send a current through the rock and the resistivity spikes, you are likely looking at oil or gas.
But notice how quickly that assumption can fall apart if you ignore the Archie context.
Oh, right. Because of the rock type?
Yes. If your gamma ray log wasn't integrated and you didn't realize you were in a dense, non-porous limestone, you might see a massive resistivity spike and assume it's oil. But the limestone itself is an insulator. That's why the tools have to talk to each other.
Okay, that makes perfect sense. Which brings us to the logs that actually measure the porosity tools. Dn is density, and NTHI is neutron porosity. These two are fascinating to me because they literally bombard the formation to get a reaction.
They do. It's active measurement. The density tool uses a gamma ray source to measure the electron density of the formation, which correlates to the bulk density of the rock.
So the denser the rock, the less pore space it has.
Exactly. And the neutron tool, conversely, emits high-energy neutrons that collide with atoms in the formation. Neutrons lose the most energy when they collide with hydrogen atoms.
And since fluids, both water and hydrocarbons, contain abundant hydrogen, and the rock matrix generally does not, the neutron log is essentially a hydrogen detector mapping out the fluid-filled pore space.
You got it. And when you lay the density curve and the neutron curve over each other, you get one of the most famous visual indicators in the industry, the crossover.
The crossover.
Yeah.
Because gas has a much lower density and a lower hydrogen index than oil or water, right?
Yes. So it causes the density log to read a very high porosity and the neutron log to read a very low porosity. The two curves cross over each other on the log plot, creating this distinct visual shape that practically screams gas zone.
But here's where it gets really interesting. That visual crossover brings us directly to the most dangerous psychological pitfall in this entire discipline.
It really does. The source material issues a vital warning right here. It calls it the common trap.
Do not let one number carry the interpretation.
Do not let one number carry the interpretation. You cannot turn why petrophysics became a discipline into a single number answer.
The single number trap. It is incredibly insidious because of human nature. We are biologically wired to look for silver bullets. Imagine you're staring at miles of complex, contradictory, well-logged data.
And you're stressed. The drilling rig is costing $100,000 a day. Management wants an answer yesterday.
And suddenly you see that beautiful density neutron crossover. It flashes at you. It perfectly confirms the theory you already had in your head that there is a massive gas cap in this block. How do we actively check ourselves to make sure we aren't falling into this trap before we publish a conclusion?
By understanding that confirmation bias is the great destroyer of technical accuracy. When a petrophysicist sees that one flashy data point and decides to build their entire presentation around it, they are no longer doing science.
They're just cherry-picking data to fit a preconceived narrative.
Exactly. They ignore the core data that might show the permeability is too low to ever produce that gas. Or they completely ignore the sonic log.
Right. Let's touch on the sonic log, SON, because that's often the reality check, isn't it? It measures the travel time of compressional acoustic waves through the rock.
Yes, sound travels faster through a solid rock matrix than it does through fluid. So it gives us both porosity data and critical information about the mechanical strength of the rock.
So if the sonic log is telling you the rock is completely unconsolidated, basically just loose sand, but you're only focusing on the gas crossover.
You're going to have a massive problem when you try to complete that well. The sand could just collapse into the wellbore.
Wow. So this is why integrated evidence is a control.
Yes. If you turn the discipline into a single number answer, you bypass the safety net entirely. An interpretation is only valid when the core samples, the geological context, and every well log converge on a single physical reality.
You actively check yourself by forcing the conflicting data to be reconciled, rather than just highlighting the data that supports your hope.
Exactly.
So we establish the context. We insist on quantitative measurements of the pore system. We integrate multiple streams of evidence to defeat confirmation bias. But, and this is a big way, but even if we execute all three of those steps perfectly, there is still a ceiling to what the science can confidently claim.
Which leads us to the fourth and final control: technical limits.
Technical limits.
This step closes the entire review sequence. It carries a 68% weight in ensuring the final interpretation holds up under scrutiny. It helps define exactly what the interpretation can and cannot claim.
So a technical claim should always remain limited strictly to what the controlling evidence actually supports. This is where we have to talk about resolution and uncertainty, right? Because a well log is not a magic wand.
No, it's not. Every single tool has physical limitations.
Let's take vertical resolution as an example.
Okay, good example.
Phew.
Many well logging tools average their readings over a vertical span of, say, 2 or 3 feet. So if you have a reservoir that consists of highly laminated, thin beds, like alternating layers of sand and shale that are only a few inches thick, the tool cannot physically resolve those individual layers. It just averages them all together.
So the tool might read a mediocre, low-quality rock, when in reality you actually have incredibly high-quality sand that's just interbedded with pure shale.
Precisely. If you ignore the technical limits of the tool's resolution, you might incorrectly condemn a highly productive zone.
Or conversely, you might calculate an exact hydrocarbon saturation to 2 decimal places, completely ignoring the fact that the tool's margin of error at that depth, under those temperature conditions, is plus or minus 10%.
Which happens all the time. But this is where the science collides with the corporate reality.
Oh yeah. Doesn't management absolutely hate hearing, "we don't know"?
They despise it. In an industry driven by multi-million-dollar investments, executives want certainty. They want a scientist to point at a map and say, the oil is exactly here, and there are exactly 10 million barrels of it.
It takes an incredible amount of professional courage to present an integrated model and then boldly state the boundaries of what you cannot prove. So what does this all mean for the final takeaway? It sounds like stating what we don't know is just as critical as stating what we do know.
It does take courage, but it is the hallmark of a true professional. And ultimately, it's what protects the economics of the company.
Because an overconfident claim based on a failure to respect technical limits is exactly how you end up drilling that $50 million dry hole we talked about at the very beginning.
Exactly. If the integrated evidence suggests there might be oil, but the technical limits of the logs have a high margin of error, maybe due to washouts in the wellbore, your conclusion cannot be, we found a guaranteed reserve.
Right. Your conclusion must be, the evidence suggests potential, but falls short of certainty due to environmental measurement limits. This final check really forces discipline over imagination.
It prevents the industry from operating on wishful thinking. And it ensures that future engineers who look back at your interpretation 10 years from now understand exactly where the hard data ended and the extrapolation began.
That is so important. So if we synthesize this practical review path for the listener, it's a sequential filter to strip away assumption and an error.
Yes. Step 1. Frame the interpretation entirely around the Archie context.
To ensure the physical setting dictates the data's meaning. Step 2. Demand quantitative thinking. Use it as a supporting control. Measure the actual grain-to-pore relationship. Do not just guess.
Step 3. Integrated evidence. Calibrate the well logs with the physical core samples to avoid the single number trap. Use them as supporting evidence rather than isolated answers.
And finally, close the review by linking technical limits to the final takeaway.
It is a methodology built on humility in the face of complex natural systems. As the text concludes, the ultimate goal isn't to memorize isolated statements or strings of numbers. The goal is to understand the rock, interpret the data.
Understand the rock. Interpret the data. It is a sequence that guarantees reality always gets the final word, rather than our assumptions. And, as we wrap up this deep dive, I want to leave you with a broader application of this framework.
The parallels to general data analysis are really striking.
They really are. If you applied these 4 controls to how you consume daily news or personal data, insisting on context, requiring measured relationships, integrating multiple sources to avoid the single number trap, and defining the absolute technical limits of what the data proves, how much more disciplined would your own worldview become?
You would be isolating the signal from the noise, defining the limits of your own certainty.
Exactly. Knowing what the data proves and having the discipline to admit exactly what it does not prove. It's a powerful framework for navigating an uncertain world. Thanks for listening to Petrophysics Daily. See you in the next chapter.